Hello, for today's video we are going to look at the motor effect. Now this can be quite tricky in places, but we'll go through it step by step and hopefully you'll get a grip of it before by the end of the video. Now the first thing is, in the last video we did about electromagnets, we looked at a simple circuit like this and we said that if we have a cell with a wire connecting positive to negative, we said that there would be a magnetic field around the wire. Be quite a small magnetic field, but there would be a magnetic field, and in effect this is now made into an electromagnet, and it has, to go along with being electromagnet, it has its magnetic field around it. Now the second thing we need to juggle in our head when we look at the motor effect is to actually look at a magnet. So here I've got a permanent magnet. It's not an electromagnet, it's just a magnet that you might have seen every day that you've played with, and if we combine this permanent magnet with our electromagnet, we get an interesting effect. So we could take our electromagnet here that we've made by putting a current through a wire, we could bring it near our permanent magnet, and you should get some effect of movement either towards or away from each other. And if in actual fact, if we just rearrange it a little bit, and if we just put our circuit like so, if we put our circuit like so, we find we actually do get some level of movement. Now before we actually look at what that movement is, we need to just consider something else about our magnetic field. So we've got our magnet here, we've got the north pole on this side and the south pole on this side, and what happens is we get a magnetic field which goes from north to south. So if I was to draw the field lines from that, you would see that they go in this direction. A magnetic field going from north to south. So in this diagram it's going from left to right. Now if we then have our electromagnet, which is also has a magnetic field around it, we find that we get some movement. We either get movement upwards or we get movement downwards, and whether it goes up or down depends on which way the magnetic field is going, and it depends on also the direction of the current, and we can look at that in a bit more detail now. Right, so here's just another version of that diagram, but what we need now to decide which way this wire is going to move, it will either move up or down. We've got to decide which way that's going to happen, and what we do is we use something called Fleming's left hand rule. And the way we do that is we have to put our left hand in a certain shape, and the shape is as shown in this diagram. Our thumb pointing directly upwards, the first finger pointing forwards, and then the second finger, or the middle finger there, pointing at a right angle to our first finger. So just as shown in the diagram there. So what I've done there is I've put in some arrows there just so you can see, but if I move those out of the way, that's what it should look like. We have thumb, first finger and second finger in this shape, and each one of those fingers or thumb tells us something about what's going on. If we put our first finger in the direction of the magnetic field and our second finger in the direction of the current, we will be able to work out the direction of motion. And the thumb tells us motion, or movement we could say, let's call it movement. And the way to remember this really is we've got thumb here, thumb with an M for movement. We've got the first finger, which first and field go together, and for the second, there's a C there, second finger is in the direction of the current. So thumb is movement, first finger is field, or the magnetic field direction, and the second finger is the direction of the current. So in this case here, the magnetic field we know goes from north to south, so it's going that way. So we can make our shape with our hand, and we can then point our first finger in the direction of the field, keeping the other finger and the thumb in exactly the same position, not moving them around. And then we can look at which way the current is going. Now current we know goes from positive to negative, so in this particular case the current will be going in that direction because it goes positive all the way around. So along the wire that's cutting the magnetic field, it's going in the direction shown. And once we've got that, we can see that the motion of the wire is going to be downwards. We have to do a little bit of fiddling around. We have to actually twist our wrist around so that the thumb's pointing downwards, the first finger is pointing in the direction of the field, and the second finger, which is supposed to be for current, is actually pointing, if you like, into the page. So we have the hand in that position there, and that tells us that the direction of motion is going to be downwards. Now it's quite fiddly having to work that out. You have to sort of do some funny twists and turns with your wrist in order to get it right, but once you've practiced on one or two, you should be able to do that. So let's just try it on one more, and there's a couple other points I want to go through. So here I've got a slightly different shaped magnet, north and south as shown. We know the magnetic field is then still similar to the last picture in this direction here, north to south. The current this time is actually going in the opposite direction, so here's our plus part of our cell, and so the current through the wire is going this way. So if you try it out, put your first finger in the direction of the field, which is the same as the last diagram. The current this time is actually coming out of the page, so you're actually pointing at yourself. If you've got your hand in the correct way, your first finger is pointing to the right, the middle finger, the second finger, you're pointing at yourself, and therefore your thumb actually should be going upwards, and that shows that the motion in this case is actually up and not down as it was in the previous one. Okay, so that gives us a clue that if we reverse the current, we're going to get a different direction of motion. The other couple of things that you do need to know also is that you can increase the force with which this wire moves up or down by increasing the current. So if we have more cells to increase the current, the force with which this wire moves up or down is increased. If we keep the current the same, we can increase the magnetic field, so in other words get a stronger magnet, and that force will then be increased. But we can also reverse the force by reversing the magnetic field or reversing the current. So instead of having north and south over here, we could have south and north the other way around. We'd then have to point our finger in the opposite direction, and we would see that we would get a different direction of motion because we've reversed the magnetic field. And the same idea with reversing the current. We kind of did that with this example here. Now what I want to do next is just go through a couple of examples where this motor effect is used, and it seems quite obvious that we would use the motor effect in a motor, but a motor, a very simple version of what a motor looks like, is on the screen here. What we have is a little circuit, so I've drawn that in blue. We've got our power supply, our cell, which is providing the current. The current is going to go from the positive to the negative. As we know, it will flow in this direction here, but it will actually then flow through the wires in the motor, which I've just drawn in black here. So it will flow through the wires in the motor in that direction. For this end of the wire, it's flowing that way, and in the other end, let's just move this out of the way, it's moving in this direction. And we can work out which way this motor is spinning based on what we just learned about Fleming's left-hand rule. So here's our Fleming's left-hand rule. That's the way the finger and thumb should be, and if we work it out for this end here, let's see which way the magnetic field is going. Well, it's going from north to south, so it's in this direction here, so that's which way your first finger should be pointing, which it is. The second finger pointing in the direction of current, which is this way, so we've got that correct as well. So the motion of, or the movement of the wire on this side is going to be upwards. That means if it's going upwards on this side, it's pretty obvious that on this side it's got to be going downwards, otherwise it wouldn't be spinning. But you can have a quick try, wiggle your wrist around until you get that right, and you'll actually notice that because of the direction of the current has reversed, the motion actually on this side is downwards. Okay, so that's just one example of where we use it. A real motor looks like this. The power or the current goes in the back actually, and the magnets are on the inside wall, and there's a very tightly wound coil inside there just to give it more spin than you would if you had a motor with just one wire here. And the last example, they do kind of mention this as a recommended thing you look at in the spec, but the last example is a speaker, and I've kind of tried to draw it in a 3D way here, but here we've got a speaker, or parts of a speaker. This part here is actually a magnet. It's a permanent magnet. We've got the north on the outside and the south on the inside, so it's made in a certain shape, so north on the outside and south on the inside. We've got a coil of wire which I've drawn in red, and that's actually wrapped around the cone as we see there, and this cone is then placed inside like so. There you go, that's a bit better. So that's my attempt to try and draw it in a 3D way, but if we sliced all of this in half and we looked at it in a slightly more simple way, you'd see it was something like this. We've got our diaphragm here think it's called a diaphragm. Anyway, the cone of the speaker here, and it's attached in the way that we've shown there, so this whole thing can move. We've got a coil of wire, and it makes sense. If this is a magnet and we put a current through this wire, we have the electromagnet in red and the permanent magnet in grey. So if the current goes in one direction, the cone of the speaker moves out. If the current goes in a different direction, the cone of the speaker moves in. And if you vary the current going in and out and the size of the current going in and out, this can move in and out, and it can make your lovely music. Okay, so that's just an overview of how that works. The key things you really need to know is how do you make it move more rapidly? Well, you have a high current going backwards and forwards, a high alternating current, so it'd be moving backwards and forwards quite a lot. And if you have a lower current moving backwards and forwards, it will be moving slightly less, and that's to do with how loud the sound might be. But anyway, that's how the loudspeaker uses the motor effect. We've looked at a motor. Hopefully this made some kind of sense. It can be quite tricky, but maybe look at it once or twice and hopefully you'll get the hang of it. But other than that, that's me done. Thank you for watching, and I'll see you again soon.